Good afternoon or good morning, whatever time of day it is, wherever you're at. I hope it's going well for you. This is going to be the last video in our simple linear regression series. This will be the fourth video. I encourage you to go back and watch the first three in order before watching this video. Now, there aren't any calculation methods or anything earth-shattering in this video. But there are some additional topics related to regression analysis that I need to make you aware of. These topics are certainly beyond the scope of an introductory statistics class. Those other topics include nonlinear regression, which I'll talk a little bit more about, multiple regression, and regression analysis, where we have a nominal level binary or dichotomous dependent variable. And I'll talk a little bit more about what I mean by that. And you're not beyond the scope of this class. If you take additional stat classes, more advanced stat classes, if you end up needing more advanced education in statistical analysis, I recommend that you take a class that just specializes in regression analysis. In that regression analysis class, you're going to talk about nonlinear regression and multiple regression, and you might even venture into a dichotomous or binary regression as well. Take that regression analysis class. You might also, and I would really encourage you to do an analysis of variance class first. We haven't talked about analysis of variance in this class. I wish we could fit it in because it really goes hand in hand with regression analysis, and there are a lot of useful methods associated with analysis of variance. So for future study, analysis of variance class and also a regression analysis class. We don't offer those at NSU, but if you end up in grad school at Oklahoma State or OU or another larger university, you'll have access to those types of specialized classes. All right, first of all, as far as other topics, let's talk about nonlinear regression, also referred to as curvilinear regression. But before I get there, got ahead of myself, when it comes to calculation methods, and I mentioned this in some of the earlier regression videos, in the real world, you will not be hand calculating any of these methods. Even simple linear regression, you will not need to do hand calculations. There are statistical analysis software packages available for the calculation of these different methods. SPS is one, SAS is another, Minitab, and there are several others also. But one thing about SPSS and SAS specifically, once you leave NSU, if you go into a job right after you graduate, if you don't go into grad school, most employers are not going to have a site license for SPSS or SAS. But most employers will have a site license for Excel. And Excel with a stat add-in is the way to go for most of you if you're not going to graduate school. There are a couple of stat add-ins that I'm familiar with. I'm not experts in either one, but one of those stat add-ins would be a Megastat, and it's designed or programmed to work with Excel. Another one of those add-ins is SPC, also programmed to work with Excel. Both of those add-ins will let you do some pretty high-level statistical analysis with Excel, and it's pretty easy to use. And the most important thing about these stat packages, they're not difficult to use, but we have to understand what's happening with those stat packages, with those calculations, and understand how to interpret those calculations. Once we get a printout of our analysis, well, what do all those numbers mean? That's the most important thing for you moving forward, is being able to interpret the different statistical methods. Now let's talk about nonlinear or curvilinear relationships and how it relates to linear regression. We've done linear regression, which really doesn't work that well if we have a curvilinear relationship like we see on the scatter diagram here. There is definitely a relationship going on, but a straight line does not fit these data. Straight line doesn't work. Now, if we use simple straight line methods like Pearson's R, we do find a strong positive correlation, 0.865. We also have pretty good explained variation with our coefficient of determination, our R squared value. We're explaining about 75% of the variation in Y using X as our independent variable. But we could do much better than these numbers here. We can come up with a line that better fits this curvilinear relationship. The way we achieve that better fit is by transforming the X variable. Transforming, what I mean by transforming, we're making some kind of operation on the X values so that the data or our regression line, our regression model better fits the data. One of the more common transformation is simply squaring the X value. Depending on the shape that appears in our scatter diagram, we might take the square root of X. There are several different transformations. Now, this particular relationship that we see exhibited here in the scatter diagram, simply squaring the X is the transformation that we need to create a model that better fits these data. If we rerun the regression analysis using X squared instead of X, we will create the equation of a line that will better fit these data and be a better predictor of Y. Using X squared in our Pearson's correlation coefficient formula returns a stronger correlation, and we also have 10% more explained variation. And here's the correlation between X squared and Y. All we did was take the X values and square each of those X values and run the correlation using X squared instead of X. And we have a stronger positive correlation between X and Y. Our explained variation also is increased, again, by about 10%, or from about, let's see, what was the number over here? From about 75% to about 85% explained variation. So the model using X squared is going to be a better predictor of Y. And again, this is just one example of possible transformations. If our scatter diagram looks like this, you might want to cube X. If our scatter diagram looks like this, you may have to take the log of X, or maybe the square root of X. Again, X to the power of 1/2 is the square root of X, same thing, they're equal. You might use a quadratic transformation, which is akin to the X squared transformation on the previous slide. And as indicated here, and believe it or not, it's as simple as trying different transformations to achieve the best fit. And we're measuring that best fit primarily by the explained variation, by our R squared value. And like I alluded to previously, if you take a more advanced class, a class that focuses just on regression, you'll get into more detail in these transformations and how to deal with curvilinear relationships. Another topic that really it's more realistic. When we are trying to understand a Y variable, when we are trying to understand virtually any phenomenon, it's not going to be just one independent variable that affects that dependent variable. There are likely to be multiple X variables involved. With multiple regression, we're building a model that includes multiple X variables, and that's indicated in this regression line. This is the form of a multiple regression line. We have our y-intercept, of course, but we have x1, and there's a beta coefficient for x1. We have x2, beta coefficient for x2, and we go all the way out to maybe 5 or 6 variables, depending on our model, that's needed to explain the y variable. Now, with multiple regression, when we calculate the beta coefficient for x1, we're controlling for the effect of x2, x3, and however many x's we have. So there's an element of partial correlation coming into play. If you go back to the video, our discussion of partial correlation, we're controlling for the effect of all these variables simultaneously on the dependent variable. Again, you're definitely not going to be doing this by hand. You're going to be using statistics software to build these multiple regression models. Now, there is a chapter in your text, if you would like to take a look at it. Chapter 14 provides a brief discussion of multiple regression. And there are some pretty good examples in there of multiple regression also. We're not covering it in class. You're not responsible for that material in class. But if you'd like to learn more about it, you're not going to take a more advanced statistics class, and you'd like to learn more about it, chapter 14, I encourage you to take a look at it. Then finally, we might run into phenomena that are measured on the nominal level. The dependent variable is yes or no, or there's other dichotomies that may be explored. One example in the business world, one thing that you might want to explore in the business world using binary logistic regression would be a prediction of whether someone will make a purchase or not. Manufacturers are certainly interested in whether consumers will purchase their product or not. So we can create a multivariate logistic regression model that would allow us to predict whether a consumer, would buy a car or a piece of stereo equipment or whatever it is the consumer is selling. So there certainly is business applications for these methods. If you would like to learn more about these dichotomous regression methods or predicting dichotomous variables, take a look at this link. And when I upload this PowerPoint to Blackboard, this link will be active. You'll be able to click on it and go to it. It talks a little bit more about logit and probit, which is a specific form of binary logistic regression. Definitely needs statistical analysis software for this level of analysis. All right, that's all I've got in this quick little video. Simple linear regression is just the beginning. I encourage you to explore more advanced statistics classes where you'll dive more deeply into curvilinear relationships, relationships where there are multiple independent variables, and relationships where we are predicting a binary or dichotomous dependent variable. All right, that's the last video in this series. As always, let me know if you have any questions. Email me, text me, or call me, or you can always talk to me in class or after class.